Question 29b. A machine produces nails. When the machine is set correctly, the lengths of the nails are normally distributed with a mean of 6.000 centimeters and a standard deviation of 0.040 centimeters. To confirm the setting of the machine, 3 nails are randomly selected. In one sample, the lengths are 5.950, 5.983 and 6.140. The setting of the machine needs to be checked when the lengths of 2 or more nails in a sample lie more than 1 standard deviation from the mean. Does the setting on the machine need to be checked? Justify your answer with suitable calculations. Now the acceptable range is 6 centimeters plus or minus 1 standard deviation, which is 0.04 centimeters. So that gives us a range of 5.960 centimeters to 6.040 centimeters. Now from the 3 nails selected, 2 nails are outside that range, 5.950 and 6.140. So that means the machine will need to be checked. Question 20. There are 60,000 students sitting a statewide examination. If the results form a normal distribution, how many students would be expected to score a result between 1 and 2 standard deviations above the mean? Now you may assume for normally distributed data that 68% of scores have z-scores between -1 and 1, 95% of scores have z-scores between -2 and 2, and 99.7% of scores have z-scores between -3 and 3. That's known as the empirical rule. Now, first thing to note is that 34% of scores lie between z-scores of 0 and 1. Since, of course, 68% lie between -1 and 1, so obviously I've halved that range there, which will mean I'll have to halve that percentage there as well. And also, half of 95%, which is 47.5% of scores, must lie between z-scores of 0 and 2. Now you can see probably what I'm about to do next. Of course, I'll need to subtract one from the other because we're interested in the number of scores between 1 and 2 standard deviations above the mean, not between 0 and 1 or between -1 and 1. So it's like working out a composite area. And to work out the number of scores, it's 47.5%. So that's the number of scores between 0 and 2. And we're going to subtract from that the number of scores between 0 and 1, and that's 34%. And we're going to multiply that by 60,000 since there are 60,000 students. And we obtain 8,100. So the answer is option A. Question 29b. Ali's class sits 2 geography tests. The results of her class on the first geography test are shown. The mean was 68.5 for the first test. Part 1. Calculate the standard deviation for the first test. Give your answer correct to 1 decimal place. Now for this you can use stat mode on the calculator. So mode, now on this one it's mode 3, and then number 1 var, and then just enter in the scores as shown. So 58, 74, 65, 66, 73, 71, 72, 74, 62, and 70. Then press AC, and press Shift, and then number 1, and then number 4, where it says var, and then option 3, that's sigma x, that's the standard deviation. It's 5.22, which is 5.2 to 1 decimal place. Part 2. On the second geography test, the mean for the class was 74.4 and the standard deviation was 12.4. Ali scored 62 on the first test. Calculate the mark that she needed to obtain in the second test to ensure that her performance relative to the class was maintained. So the strategy here is to determine Ali's z-score for test number 1, then assume that Ali's z-score for test number 2 is identical to her z-score for test number 1, and then use the z-score formula in such a way as to determine her raw score so that the z-score for test 2 is equal to the z-score for test 1. So the first thing we're going to do is determine Ali's z-score for test 1. And using the z-score formula, it's 62 minus 68.5. So that's her raw score minus the mean for test 1 divided by the standard deviation for test 1. And that equals negative 1.25. Now the next step is to determine the raw score that Ali should achieve such that the z-score for test number 2 is also equal to negative 1.25. So again, using the z-score formula, negative 1.25 is equal to Ali's raw score, which at this point is unknown, minus 74.4, that's the mean for the class for test number 2, divided by the standard deviation for test number 2, which is 12.4. And then we're going to solve for x. So I'm going to rearrange this formula, make x the subject. So multiplying both sides by 12.4, we have negative 1.25 multiplied by 12.4 is equal to x minus 74.4. And of course, we're going to add 74.4 to both sides so that x is the subject of the formula. So we end up with negative 1.25 multiplied by 12.4 plus 74.4 equals x. So therefore, x is equal to 58.9. So let's round that to the nearest whole number. Ali would need to score 59, which is correct to the nearest whole mark. Question 24. The weights of 10,000 newborn babies in New South Wales are normally distributed. These weights have a mean of 3.1 kilograms and a standard deviation of 0.35 kilograms. How many of these newborn babies have a weight between 2.75 kilograms and 4.15 kilograms? Now, the first thing to note is that the weights are normally distributed, which means I'm going to use z-scores to find the percentage under the normal distribution that corresponds to these two weights. So let's find the z-score for 2.75 kilograms. So I'll call that Z1 is equal to 2.75 minus the mean, 3.1, divided by the standard deviation, 0.35, and that gives us negative 1. And likewise, the z-score for 4.15 kilograms is calculated in a similar way. So I'll call it Z2, is equal to 4.15 minus 3.1 divided by 0.35, and we get a z-score of 3. So if we visualize that on the normal distribution, okay, so there's a z-score of negative 1, z-score of positive 3, and the percentage under the normal distribution between these two z-scores can be worked out this way. Between negative 1 and 0, we know there's 34%. And between 0 and 3, the way I work that out is, I know that 99.7% of the data lies between negative 3 and positive 3. You can get that from the reference sheet. Dividing that by 2, because we're only interested in 1/2 of the normal distribution, and that gives us 49.85% in this region. So the number of babies is equal to 10,000, so that was the number of babies surveyed in terms of their weights, multiplied by the sum of these two percentages, so 34% plus 49.85%, I'll just put that in brackets. Multiplying that together, we get 8,385 babies that lie between the two weights specified, and that's option D. Question 20. A machine produces cylindrical pipes. The mean of the diameters of the pipes is 8 centimeters and the standard deviation is 0.04 centimeters. Assuming a normal distribution, what percentage of cylindrical pipes produced will have a diameter less than 7.96 centimeters? So this is a question based around the bell curve, around the normal distribution. Now it's interesting to note that 7.96 centimeters is one standard deviation below 8 centimeters. In other words, its z-score is negative 1. Okay, and that's actually easy to work out. First of all, let's quickly do that. Z-score is equal to 7.96, the raw score minus the mean over the standard deviation over 0.04. Okay, and if you want to quickly work that out, 7.96 minus 8 over 0.04, and we have a z-score of negative 1. Okay, so you can refer to the formula sheet, but I'm just going to draw just a bell curve here quickly. Okay, so there's a z-score of 0, which represents the mean. Okay, that's the mean of 8 centimeters. So that's Z. And here's a Z score of -1. Now, we know that 50% of the scores lie basically on sort of in each half of the bell curve, either side of this Z score of 0. We also know that between -1 and 0, we have 34% of the scores, which leaves the balance of 16% of scores that lie basically from -infinity, sort of all the way to one end of the bell curve, to a Z score of -1. And this -1 refers to, or is represented by 7.96 centimeters. So the answer is A, 16%. Question 28b. The results of two tests are normally distributed. The mean and standard deviation for each test are displayed in the table. Christoph scored 74 in mathematics and 80 in English. He claims that he has performed better in English. Is Christoph correct? Justify your answer using appropriate calculations. So what we need to do is compare the Z scores that correspond to 74 and 80, and obviously the Z score that's higher. The raw score that is represented by that Z score would then be the better score, or the highest score. So especially if we're comparing relative performance in sort of two different subjects, that's what we need to do. Okay, so let's work out the maths Z score. Okay, so we take Christoph's raw score, 74, and we minus the mean over the standard deviation, which is 6.5. Okay, and let's see what value we get. So 74 minus 70 divided by 6.5, and we get 0.615, or thereabouts. So 0.615. So it is sort of approximately equal to. Okay, now let's work out the English Z score. Okay, so Christoph scored 80 in English, and the mean for English was 75, and we divide that by standard deviation of 8. Okay, and we'll see approximately what that evaluates to. Okay, so 80 minus 75 over 8, and we get 0.625. Okay, so the English Z score is greater than the maths Z score. Hence, Christoph is correct. Question 13. The speed limit outside a school is 40 kilometers per hour. Year 11 students measured the speed of passing vehicles over a period of time. They found the set of data to be normally distributed with a mean speed of 36 kilometers per hour and a standard deviation of 2 kilometers per hour. What percentage of the vehicles passed the school at a speed greater than 40 kilometers per hour? So 36 is the mean. I might just draw a quick number line. So if 36 is the mean, okay, we have two standard deviations. So a standard deviation is worth 2. So that's 38 kilometers an hour, 40 kilometers an hour. So we actually want the part of the bell curve that's a Z score of 2 or higher, or the area under the normal curve. Now, it's always a good idea to sort of fill this in at some point. Z score of 2 or more. Okay, so that corresponds to 40 kilometers an hour or greater. So it's going to be 2.35 plus 0.15. That's going to be 2.5%. Option A. Question 30D. The formula to calculate Z scores can be rearranged to give x bar equals x minus sz, where x bar is the mean, x is the score, s is the standard deviation, and z is the Z score. Part 1. In an examination, Aaron achieved a score of 88, which corresponds to a Z-score of 2.4. Substitute these values into the rearranged formula above to form an equation. Okay, so we don't know the mean, we don't know the standard deviation, okay, but we do have the raw score and we do have the Z-score. So that'll be X bar is equal to, now X is the raw score, so Aaron achieved 88, minus S multiplied by the Z-score of 2.4. And we could just simplify that just a little bit further, minus 2.4 S. Part 2. In the same examination, Brock achieved a score of 52, which corresponds to a Z-score of negative 1.2. Using this information, form another equation and solve it simultaneously with the equation from part 1 to find the values of X bar and S. Okay, so let's form another equation. So this is Brock's score. Okay, and we have X bar is equal to, now Brock achieved a raw score of 52 minus standard deviation multiplied by Z-score of negative 1.2. Okay, now might just simplify that. So minus S multiplied by minus or negative 1.2. So that'll actually make it plus, and minus multiplied by a minus, or a negative times a negative result in a positive. So that's 1.2 S. Okay, and now we're going to solve it simultaneously with this equation here, the one that we came up with in part 1. Okay, so from part 1, we have X bar is equal to 88 minus 2.4 S. Okay. Now we could either use elimination or substitution method. Actually, it doesn't really matter. We have X bar is equal to 52 plus 1.2 S. X bar equals 88 minus 2.4 S. These two X bars are the same. It's the same mean. It's the same group of data. So it's exactly the same average. So if the two left-hand sides are equal, that means the two right-hand sides must also be equal. So 52 plus 1.2 S is equal to 88 minus 2.4 S. So what we're going to do is solve for the standard deviation, and then we can solve for the mean. So sort of knocking out one of the variables. Okay, let's move everything over to one side. So 1.2 S plus 2.4 S is equal to 88 minus 52. Okay. So 1.2 plus 2.4 should give us 3.6 is equal to 88 minus 52, and that gives you 36. That's very convenient. Okay. So S is equal to 36 divided by 3.6, which equals 10. So that's our standard deviation. So X bar, and we can use any equation we like. We could use top equation, which doesn't really matter, or this equation here. In fact, let's just use this one, probably just as easy. Is equal to 52 plus 1.2 multiplied by S, which we've now found is equal to 10. So evaluating that, okay, so 52 plus 1.2 multiplied by 10 is equal to 64. Okay, so therefore X bar is equal to 64, and the standard deviation is equal to 10. Question 13. The heights of Year 12 girls are normally distributed with a mean of 165 centimeters and a standard deviation of 5.5 centimeters. What is the Z-score for a height of 154 centimeters? Now, 154 centimeters is less than the mean of 165 centimeters. That immediately implies that the Z-score has to be negative. So it can't be option D or C. So if you had to guess, obviously A or B. We can use the formula. Z-score is equal to the raw score, which is 154, minus the mean of this set of data, which is 165, over 5.5. Okay, entering in that expression in the calculator, 154 minus 165 over 5.5, and we get negative 2. Option A. Question 29D. All the students in a class of 30 did a test. The marks out of 10 are shown in the dot plot. So part 1, find the median test mark. So the median test mark is just the middle score. We know that 30 students did a test, so we need the mean of the 15th and 16th scores. So just remember, with median, if there's an even number, you need the mean of the two middle scores. So let's count 15 scores. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So the median, okay, is equal to 4 plus 8 over 2, which is equal to 12 over 2, which equals to 6. Part 2. The mean test mark is 5.4. The standard deviation of the test marks is 4.22. Using the dot plot, calculate the percentage of marks which lie within one standard deviation of the mean. So we need to work out what that range is. So, okay, so the lower limit, okay, is equal to 5.4 minus 4.22. Okay. So 5.4 minus 4.22, and we get 1.18. Okay, let's work out the upper limit, which is equal to 5.4 plus 4.22, which equals to 9.62. So let's count the number of scores that lie between these two values. So we can't include 1 since the score of 1 is in fact less than 1.18. So it's from the 2s, okay, so from the mark of 2 onwards. And we can't include 10 since obviously 10 is greater than 9.62. So these are counting the scores, counting from 2 to 9. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we need the percentage of marks. Okay, so (13 on 30 multiplied by 100), and that gives us 43.33%. Correct to 2 decimal places. In part 3, a student states that for any data set, 68% of the scores should lie within one standard deviation of the mean. With reference to the dot plot, explain why the student statement is not relevant in this context. And it comes down to the shape of this plot, that for the student's claim, or for the student statement to say that 68% of the scores should lie within one standard deviation, that implies it must be a bell curve. Okay, so the data is not normally distributed. Okay, does not follow. Okay. So I use the bell curve in quotes, but it just highlights what we mean by that. So this is the bell curve. Question 23. A set of data is normally distributed with a mean of 48 and a standard deviation of 3. Approximately what percentage of the scores lies between 39 and 45? So let's draw a number line to represent these values. Okay, so there's the mean. I'm going to put the mean up here. So that's the mean of 48. Let's subtract one lot of standard deviation, and that'll give us 45. Now this happens to be a z-score of -1. Now if we go down another standard deviation, we get 42. That's a z-score of -2. If we go down another standard deviation, which gives us a score of 39, its z-score is -3. So what we want is we want the percentage of scores that lie between these two values, between a z-score of -1 and a z-score of -3. Now hopefully you would have prepared one of these already, okay? And I do have a video on preparing one of these, okay? Adding in these percentages on top of the normal distribution. So we want these two percentages there, 2.35 plus 13.5. So that's going to be 15.85%, which is option A. Question 27E. Joanna sits a physics test and a biology test. Part 1. Joanna's mark in the physics test is 70. The mean mark for this test is 58 and the standard deviation is 8. Calculate the z-score for Joanna's mark in this test. So z-score is equal to her score minus the mean over the standard deviation. So that's going to be equal to her mark, which is 70, minus the mean, which is 58, over 8. And entering in that expression in the calculator to evaluate it, over 8. And we get 3 on 2, which is 1.5. So, part 2. In the biology test, the mean mark is 64 and the standard deviation is 10. Joanna's z-score is the same in both the physics test and the biology test. What is her mark in the biology test? So now we're going to reverse this formula and we're going to solve for x. So she had the same z-score, so 1.5 is equal to whatever her mark was in the biology test minus the mean of that biology test, which is 64, over the standard deviation of that biology test, which is 10. Now we're going to rearrange the formula. We're going to take the 10 here, we're going to multiply the 1.5 times 10. So 1.5 times 10 is equal to x minus 64. This minus 64, we're going to move that over by adding 64 to the other side. So 1.5 times 10 plus 64 is equal to x. And x is her raw mark in biology. Therefore, x equals, okay, so 1.5 multiplied by 10 plus 64 is 79. Okay. So her biology mark is 79. Question 15. The scores on an examination are normally distributed with a mean of 70 and a standard deviation of 6. Michael received a score on the examination between the lower quartile and the upper quartile of the scores. Which shaded region most accurately represents where Michael's score lies? Now, first thing to note is the standard deviation of 6 and the mean of 70. Plus or minus one standard deviation is 68% of the scores. Michael received a score, however, between the lower quartile and the upper quartile of scores. So this is the middle, or this represents the middle 50% of scores. So For example, let's have a look at option A. Between 64 and 76 is 68% of the scores. But Michael achieved a mark in the middle, 50%, which should be inside 64. So it should be greater than 64, but less than 76. So it looks like option A is in fact the correct answer. Just while we have some time, let's have a look at option B. Option B is incorrect because from 64 to 76, this is 68. Again, 68% of the scores lie between here and here. Option C, this is beyond plus or minus 1 standard deviation. In fact, this is greater than 68% of the scores because we've actually gone beyond plus or minus 1 standard deviation. All right? If you were to draw a box and whisker plot, going from Q1 to Q3, lower quartile to upper quartile, has 50% of the scores. Again, should be inside 64 and 76. And clearly D is totally incorrect. That's just above a mean of 70. So that makes no sense at all. Question 38. In a particular country, the birth weight of babies is normally distributed with a mean of 3,000 grams. It is known that 95% of these babies have a birth weight between 1,600 grams and 4,400 grams. One of these babies has a birth weight of 3,497 grams. What is the Z-score of this baby's birth weight? So the first thing to note is we have 95% of these babies have a birth weight between 1,600 grams, 4,400 grams. 95% of scores on a normal distribution lie between Z equals -2 and Z equals +2. So that's -2 standard deviations to +2 standard deviations. So 4 standard deviations is equal to 4,400 minus 1,600. Okay. So 4,400 minus 1,600, and we have 2,800. Okay. Therefore, one standard deviation is equal to 2,800 divided by 4, which equals 700. Now that we've found the standard deviation, we can then proceed to find the Z-score of this particular baby. So Z-score for 3,497, and we're going to use the formula for Z-score, which is the raw score, 3,497, minus the mean, which is 3,000 grams, over 700, 3,497 minus 3,000 over the standard deviation that we just found, which is 700, and we get 0.71, positive 0.71. Question 8. John recently did a class test in each of the 3 subjects. The class scores on each test were normally distributed. The table shows the subjects and John's scores, as well as the mean and standard deviation of the class scores on each test. You can see the table there, have a quick read of that. So relative to the rest of the class, which row of the table below shows John's strongest subject and his weakest subject? So this is a case of Z-scores. So how do we know it's Z-scores? Well, we're told that it's normally distributed. As soon as you see that, you know it's going to involve something to do with the bell curve normal distribution, Z-scores, all that sort of comes into it. Okay, so the higher the Z-score, the further along, or the higher, maybe think of it in terms of rank or strength, the subject would be for John. All right, so let's work out each one of these. So the Z-score formula, and this will be on your formula sheet, but I'm just going to write it here. So Z is equal to X, so the score, minus the mean, okay, over the standard deviation. All right, so using that, let's work out the Z-score for each one of these subjects. Okay, so the first one, French, so that's 82. Okay, so using the Z-score formula, minus the mean, so 70 over the standard deviation of 8, and we get a Z-score of 1.5. So Z equals positive 1.5. So I like to put the plus sign there, so I know clearly it's a positive Z-score. Yeah. Now, commerce. Okay, so let's do the same thing. Okay. Yep. All right, so John's score 80 minus the mean over 5, and we get a Z-score of positive 3. In fact, positive 3 is fantastic. That's a great Z-score. that's well ahead. All right, and music, 74, mean of 50, standard deviation of 12. Okay, so relative to the mean, okay, and might just 74 minus 50 over standard deviation of 12, and this is a Z-score of 2. Positive 2. So looking at these Z-scores, the lowest Z-score, even though it's a positive Z-score, it's above 0, we're talking relative. So we're talking compared to each other. French is the weakest subject. Okay, so it's either going to be this one or this one here. So it can't be B and it can't be D. Okay, so out of A and C, the strongest subject is commerce. So it's going to be option A. Question 35. The intelligence quotient IQ scores for adults in City A are normally distributed with a mean of 108 and a standard deviation of 10. The IQ scores for adults in City B are normally distributed with a mean of 112 and a standard deviation of 16. So this question has 3 parts, so I'll just quickly go through those parts. So part A, Yin is an adult who lives in City A and has an IQ score of 128. What percentage of the adults in this city have an IQ score higher than Yin's? We go on to part B. There are 1 million adults living in City B. Calculate the number of adults in City B that would be expected to have an IQ score lower than Yin's. And the final part, part C, Simon, an adult who lives in City A, moves to City B. The Z-score corresponding to his IQ score in City A is the same as the Z-score corresponding to his IQ score in City B. By first forming an equation, calculate Simon's IQ score. Give your answer correct to 1 decimal place. All right, so let's go back to the beginning. Part A. Okay. Now, this is to do with the normal distribution. So this is the bell curve. Now you can use your formula sheet. Obviously, it's got the empirical rule. Now I've just hand drawn it here, so I've just drawn it manually. Okay, so I'll be referring to this, so you might recall this. When you're dealing with Z-scores, and especially with normal distributions, anything sort of between -1 and 1 standard deviation from the mean, 68 or roughly 68% of the scores will lie between -1 and 1 standard deviation from the mean, or a Z-score of -1 to 1. 95% of scores will lie from -2 to 2, and 99.7% of scores will lie from -3 standard deviations to 3 standard deviations from the mean. All right, so we'll refer to that later. All right, so let's go back to part A. Yin is an adult who lives in City A, has an IQ score of 128. What percentage of adults in this city have an IQ score higher than Yin's? Okay, so let's see, first of all, City A, let's go back to the question. City A, the mean is 108 and a standard deviation of 10. Okay, so let's work out Yin's Z-score. Okay, and that's going to be equal to his IQ score, so that's 128. Okay, minus the mean or the average Z-score. So again, for City A, mean of 108, so 128 minus 108 all over the standard deviation, which is 10. Okay, so you could work this out easily enough. So 128 minus 108 over 10 gives us a z-score of 2. Now, it's asking for what percentage of the adults in this city have an IQ score higher than Yin's. Okay, so let's go back to our bell curve or our normal distribution. Okay, so we've got a z-score of 2. Okay, so what percentage will that be? Okay, so 2.35 plus 0.15, right, that's going to be 2.5%. Okay. Okay, so okay. Next part, part B. There are 1 million adults living in City B. Calculate the number of adults in City B that would be expected to have an IQ score lower than Yin's. So now again, if we go back to our distribution, okay, so Yin's score, his IQ score is 128. So I'll go back to the question there. Okay, so his IQ score is 128. Okay, now we're dealing with City B, so mean of 112, standard deviation of 16. So what we're going to have to do is we're going to have to recalculate Yin's z-score for City B. It's not necessarily going to be the same as City A. In fact, it won't be. Okay, so let's do that first. So right, for City B is equal to his IQ, which is still 128, minus the average for City B, and for City B, mean of 112 over standard deviation of 16. Okay, so make sure that you put in the right, substitute in the right values into the z-score equation. Okay, and that's going to be equal to, okay, so 128 minus 112 over 16, and we get 1. That's a very convenient z-score. Okay, so if we look at our bell curve, okay, so there's our standard deviation of 1. Okay, now 50% of the data lies from 0 all the way to sort of negative infinity. Okay, but we're adding another 34% to 50%. So that'll be then the total or the percentage of adults that are under a z-score of 1. Okay, so okay, first of all, so from the bell curve or from the normal distribution, okay, you've got 50%, that's percentage of scores under 0, plus 34%, which is the percentage of scores from 0 to 1 standard deviation. Okay, and that'll be 84%, and therefore 84% of adults have an IQ less than Yin's. Now that doesn't quite answer the question. We actually want the number of adults, so 84% of 1 million, okay, is going to be equal to 840,000 adults. Okay. Right, let's go to the final part now, part C. Okay, Simon, an adult who lives in City A, moves to City B. The Z-score corresponding to his IQ score in City A is the same as the Z-score corresponding to his IQ score in City B. By first forming an equation, calculate Simon's IQ score and give your answer correct to 1 decimal place. So first of all, we're going to let A equal Simon's IQ score. Okay. You could use any pronumeral you like, so it doesn't really matter. I could use the letter X. I didn't use the letter X, so not to confuse it with the mean. Okay, so the mean with the X with the bar on top. Okay, so what we're going to do is we're going to sort of form an equation. So, in other words, the Z-score for both cities is going to be the same. So the way we're going to do this is we're going to say A minus the average for City A. So just bring back, make sure you may have to go back to this, it's on a previous page. So the mean for City A is 108, standard deviation of 10. Is equal to his Z-score for City B. So A minus, now for City B, 112, standard deviation of 16. A minus 112 with A, standard deviation of 16. So we've now formed our equation. So these are the two Z-score equations basically, but with the different values substituted in, okay, for both cities. And A is Simon's IQ. All right. So now we need to solve this equation. Okay. So from this point on, it's just algebra. So what I'm going to do is I'm going to cross multiply. So move the 16 over here. So 16 A minus 108 is equal to 10 outside of A minus 112. Okay. So notice that's a very quick way to eliminate the fraction, or to convert it from in fractional form to sort of linear form, okay, without the fraction. Expand the brackets, so 16A minus, now 16 times 108, so expand that, 1728. 1728 is equal to 10A minus 1120, so that's 10 times 112. Now let's collect the like terms, so 16A minus 10A is equal to negative 1120 plus 1728. So it's just algebra really from this point on. 16A minus 10A, that's 6A. And negative 1120 plus 1728, and that's equal to 608. Now, A is equal to 608 divided by 6. Okay, so divide that by 6, and we get 101 and a third, or 0.333. Okay, sort of carries on there. And it says correct to 1 decimal place. Yep. Okay, so let's enter to 1 decimal place. So therefore, A is equal to 101.3. So Simon's. And that's it. Thank you for watching. Question 8. On a test, Zach's mark corresponded to a Z-score of 2. The test scores had a mean of 63 and a standard deviation of 8. What was Zach's actual mark on the test? Let Zach's actual mark be X. Using the Z-score formula, solve for X. 2 equals X minus 63 divided by 8, where the Z-score is 2, the mean of the scores is 63, and the standard deviation of the scores is 8. Multiplying both sides by 8, we have 2 multiplied by 8 equals X minus 63. And adding 63 to both sides to make X the subject of the formula, we have 2 multiplied by 8 plus 63 equals X. Therefore, X equals 79. So Zach's actual mark was 79. Therefore, the answer is option D. Question 38. A random variable is normally distributed with mean 0 and standard deviation 1. The table gives the probability that this random variable lies between 0 and z for different values of z. The probability values given in the table for different values of z are represented by the shaded area in the following diagram. Part A. Using the table, show that the probability that a value from a random variable that is normally distributed with mean 0 and standard deviation 1 is greater than 0.3 is equal to 0.3821. The area under the normal distribution above z equals 0 is equal to 0.5. The probability that z is greater than 0.3 is equal to 0.5 minus the probability that z lies between 0 and 3. Referring to the table, where z is equal to 0.3, the probability is 0.1179, which is represented as the shaded area in the diagram. So the probability that z is greater than 0.3 is equal to 0.5 minus 0.1179, and that equals 0.3821 as required. Part B. Birth weights are normally distributed with a mean of 3,300 grams and a standard deviation of 570 grams. By first calculating a z-score, find how many babies out of 1,000 born are expected to have a birth weight greater than 3,471 grams. The z-score corresponding to a birth weight of 3,471 grams may be found using the z-score formula. 3,471 minus the mean birth weight of 3,300 divided by the standard deviation of the birth weights, which is 570. And that equals 0.3. Now the probability that z is greater than 0.3 is equal to 0.3821, and that was found in Part A. 1,000 multiplied by 0.3821 is equal to 382.1, which equals 382, correct to the nearest whole number. So therefore, out of 1,000 babies born, 382 are expected to have a birth weight greater than 3,471 grams. Question 41. In a particular city, the heights of adult females and the heights of adult males are each normally distributed. Information relating to two females from that city is given in Table 1. The means and standard deviations of adult females and males in centimetres are given in Table 2. A selected male is taller than 84% of the population of adult males in this city. By first labelling the normal distribution curve below with the heights of the two females given in Table 1, calculate the height of the selected male in centimetres, correct to 2 decimal places. By the empirical rule, a female of height 175 centimetres is 2 standard deviations above the mean, and a female of height 160.6 centimetres is 1 standard deviation below the mean. There are 3 standard deviations in between 160.6 and 175. The standard deviation of the female population, sigma f, is equal to 175 minus 160.6, so that's the difference between these two heights, divided by 3. So sigma f is equal to 4.8 centimetres. Mu f, or the mean of the female population, can be found by taking 160.6 and adding 1 standard deviation to that value. So 160.6 plus 4.8 is equal to 165.4 centimetres. Referring to Table 2, the mean of the male population is equal to 1.05 multiplied by 165.4, which equals 173.67 centimetres. And the standard deviation of the male population is equal to 1.1 multiplied by 4.8, which equals to 5.28 centimetres. By the empirical rule, a male taller than 84% of the population of adult males has a z-score of positive 1. Therefore, the height of the selected male is the mean of the male population plus 1 standard deviation, which equals 178.95 centimetres.